for.
Okay, yeah, we're very happy to have Katelin Schutz, currently from MIT. She did her PhD in Berkeley, was a Pappalardo Fellow at MIT, and is moving to McGill as a junior faculty member in 2021. We're very happy to have her here, and she's going to tell us about making dark matter out of light, the cosmology of sub-MeV freezing.
Yeah, well, thanks so much for the kind introduction and for inviting me to give this seminar today. You know, in light of current events, hope to provide just a little bit of a distraction from what's going on in the world and tell you about making dark matter out of light, which is something that at the face of it sounds a little bit oxymoronic in a certain way. My goal is that by the end of this seminar, not only will this oxymoron make a little bit more sense, but I'm hoping to show that this is a theory that is highly self-consistent, which has, you know, a full cosmological history that makes sense, and it's also something that's highly testable both in the lab as well as using cosmological observables. Before I get going, I really just want to point out my excellent collaborators, Tongyan Lin and Korod Forkin, so kudos to them. Okay, so I think this statement probably needs very little justification to this audience. Whoops. Oh no. Oh, there we go. So the statement is that dark matter exists and it's dark. And this is, you know, a statement that we have lots of great empirical evidence for, which I'll highlight some examples of that. I want to note that I'm putting an asterisk on the statement that dark matter is dark, because currently that's something that's a little bit of an assumption that we make when we talk about dark matter. And from a purely empirical standpoint, this is something that we can only ever put an upper bound on experimentally or observationally. So, you know, dark matter could be not dark to a small extent, and that's something that's perfectly allowed. And as we'll see, that'll have some really interesting consequences. But okay, given that this statement we think it's a good approximation is true, I want to just really quickly flash through some examples of systems where we see good evidence for this. One of them, I think, in particular at UC Davis, needs very little introduction since you have Marusha Bradach on the faculty there. But here, you know, you're seeing, just as a quick review, you're seeing a picture of the bullet cluster, which is one example of two merging galaxy clusters. And we're looking at the aftermath of this merger. So this, you know, a smaller galaxy cluster has ripped through a bigger one and has left, you know, this imprint that we see. So this is a composite image where in pink, I'm showing you basically where the regular matter is in this picture. This regular matter, as this merger is happening, is heating up considerably due to, you know, things like shock heating, basically because the merger is happening and it's highly supersonic. So the gas just gets incredibly heated by this non-thermal motion of these two galaxy clusters. So hot, in fact, that it's emitting thermally in the X-rays, and that's why we can see it with the Chandra Space Telescope. And then in blue, what you're seeing is where the majority of the mass is in this picture. And that's inferred using gravitational lensing of background galaxies. And the really crucial point to note about this picture is that the pink regions and the blue regions are not co-located. They're not overlapping with each other. And the interpretation of that is, well, as these galaxies were, or galaxy clusters, excuse me, were merging, right, on a particle by particle basis, the regular matter that's shock heating and getting heated up, the reason it's able to heat up is because on a particle by particle basis, you're able to exchange momentum and convert basically this bulk velocity into something that's thermalized. So, you know, what you require for that to happen is these particles need to have some way of transferring momentum between each other. And what that's also doing, in addition to heating up the normal matter, is it's also slowing down this matter. It's causing basically a drag force between these two clouds of regular baryonic matter. And so you can see that these two clouds are sort of lagging behind where the blue regions are. That corresponds to the dark matter. And this sort of picture gives really strong evidence for dark matter not having very much of an ability to, on a particle by particle basis, have a strong ability to do momentum transfer. So in other words, you know, we can use pictures like this, like the bullet cluster and the dozens of other merging galaxy clusters that we know about to set a limit on dark matter interactions, both with itself and with baryons. Moving to even larger scales, when we look at the cosmic web of large scale structure, what we see is actually quite clumpy. And it turns out that things simply don't cluster as well when they're made only of baryons. And that has largely to do with the initial conditions of what seeded these perturbations, which ultimately then go on to become this cosmic web. So I think these initial conditions, I think, are best explained also from a phenomenon that you can see in the CMB, which is that, in the early universe, when things are optically thick, right, you have competing effects between things wanting to cluster, but at the same time, the photons and the baryons are tightly coupled to each other, right? So, things try to cluster, but the photons basically bounce baryons out of gravitational potential wells. So baryons are not very good at seeding structure formation. But meanwhile, we have dark matter, which does not really get pushed around by this photon baryon plasma. It's able to cluster sort of unhindered. And so that actually provides the gravitational potential wells for the baryons to later fall into. And I'll go into more detail about this later. But given all of this broad evidence, right? So this is, I'm a particle physicist. I gather this is an audience of particle physicists. And so we really care about this question of what is the dark matter. And in my research, I take a fairly empirical point of view on this question. And so from a purely empirical point of view, it's quite a broad space of possibilities. So if I just focus on one parameter, which is the dark matter mass, it turns out there's over 90 orders of magnitude in mass that dark matter can be if it's made only of one thing. So the constituents of dark matter could be ultralight bosons, which would have a really, kind of different phenomenology and would exhibit wave-like behavior on the scales of galaxies on the very, very low mass end. That's one qualitatively different kind of dark matter model, moving up through kind of the usual particle candidates and then going all the way on the extreme right end, thinking about compact objects as dark matter. So there's really quite a diversity of qualitatively different theories here. And you might be wondering, well, why do I need all these theories? I have, kind of my most famous, most textbook example, I have WIMPS. And so just want to really quickly go through why WIMPs are so compelling, at least from my perspective, and just really briefly review the status of these things. And I'm going to do that in part because I want to really compare and contrast another dark matter production mechanism with this WIMP one. So I want to make sure we're all on the same page here. So just to give a lightning review, so WIMPs are generally a thermal dark matter candidate that has its abundance set by a mechanism called freeze out. And what happens is that very early times, very high temperatures, at temperatures exceeding the mass of this particle, the dark matter is in thermal equilibrium with the standard model. And so its number density scales like temperature cubed, just on dimensional grounds. So if you factor out the volume, you factor out the expansion of the universe, it has a constant co-moving density. But that can't persist forever because as the universe expands, it's also cooling down. At some point, the temperature drops below the mass of these particles, which means that if there's some sort of process that can deplete the number density of dark matter, for example, I've depicted here 2-to-2 annihilation, if there's some process like that that's active, then you'll start riding this sort of exponential Boltzmann curve down, and you'll start depleting the dark matter number density more and more. But this can't persist forever because, for example, to do 2-to-2 annihilation, these dark matter particles need to be able to find each other. And that becomes harder and harder because A, their number density is dropping, and B, the universe is expanding, which is making it harder and harder for them to basically overcome that expansion. And so at some point, this process no longer becomes active. And at that point, we say that the dark matter number density freezes out and it becomes constant again. So then basically that means that the co-moving density is fixed. Now, it just so happens if you plug in a weak scale mass, so mass of order 100 GeV, and a weak scale coupling, you get something, you get a density at the end of the day that is very remarkably similar to what we actually observe in our universe. And in some sense, that's a miracle because, you could have put in any numbers and, for example, in this plot, right, these different shaded regions correspond to what would happen if you change the cross section by an order of magnitude. You get an order of magnitude different density of dark matter, potentially even overclosing the universe. So, there's no reason to expect that we would plug in a known scale in physics and out would pop something that matches observables, given that there are so many orders of magnitude that it could have been different by. And so that's the WIMP miracle. And in addition to having other motivations, let's say, for physics at the weak scale, I think that's partly why we've put so many eggs into this basket of looking for WIMPs. In addition to this thermal history, this has a lot of nice properties. So first of all, the story that I just told you is totally independent of the initial conditions, just as long as dark matter has a strong enough coupling to the standard model such that it's part of a thermal bath. So you could have started with no dark matter, and then the standard model bath would have thermalized it and would have created that population. You could have started with too much dark matter, and it would have again thermalized. So you're really insensitive to initial conditions here. This sort of process is also fine with any early universe observables that we have, so long as the dark matter is heavier than a few MeV. More on this point later. And then finally, we have this whole really rich program to experimentally look for signatures of dark matter that was made this way. So I think, really briefly, the most direct way of looking for this is actually through indirect detection. So it's ironic because of the name. But what indirect detection is doing is trying to look for this kind of annihilation process, which would be the same process responsible for setting the dark matter number density in the early universe. Now, the WIMP the WIMP mechanism lies on this sort of, oops, I have my mouse here. This is the WIMP line, which corresponds to the cross section as a function of mass that you would need to give you the amount of dark matter that we observe. If you're above it, then you don't make enough dark matter. And if you're below it, you make too much dark matter. So this is a really concrete, really predictive line in this parameter space. Now the low mass end here is constrained by dark matter annihilating into visible things that we would have seen. And meanwhile, we have this famous unitarity limit up here. So really, we have this really finite window where WIMPs are still viable. And I think closing this window from an indirect detection standpoint over the next few years is rather futuristic. Like it's probably not going to happen within the next decade or so. So luckily, though, we have a whole other program using direct detection to try to look for dark matter scattering on standard model particles. And here's an out-of-date plot from the SNOMAS 2013 report, just kind of giving a very broad overview of this space of different experiments looking in this mass range of 10 plus GeV. And many of these lines, which were dashed at the time because they were projections, are now solid because these experiments have worked fantastically. They've worked to spec, and so we've really carved out a lot of the parameter space. One caveat here, though, is that the way that you equate annihilation in the early universe to scattering in the lab is highly model dependent. So, you can carve out all this parameter space that you want, but it's really hard to conclusively rule out WIMPs because you basically introduce all sorts of model dependence where you can make it so that you have WIMPs in the early universe having efficient annihilation, but then the scattering is somehow suppressed. So, for that reason, you sometimes hear people say the WIMP is dead or the WIMP is not dead. That's kind of my big picture on why that is. So I think a large fraction of the community is thinking about going beyond this paradigm, partly because the weak scale could just be a coincidence of nature, and there's precedent for that in the history of particle physics. For example, Rabi famously said, "Who ordered the muon?" Right? Because there was, we were expecting new physics at sort of the 100 MeV scale, right? And people thought that this had something to do with the strong force, and it turns out the muon is just a heavy electron. So Rabi said, "Who ordered that?" And moreover, the standard model isn't minimal. So why should the dark matter be minimal? There could be other things going on. And then in my mind, one of the most compelling reasons to think about this is just that a lot of new technologies and observations are coming online and allowing us to probe different kinds of models. And so on the theory side, we had better be prepared for that. So with that, I want to sort of take a deep dive on a different mass range in sort of KeV to MeV scales. And really emphasize the power of astrophysical systems in this space. So with that, I'll tell you without further ado about making dark matter out of light. This is going to turn out to be an example of a thermal-ish dark matter scenario called freeze-in. So, just to get right to the point, inside of a medium, photons, it turns out, can actually decay to particles, provided that those particles are A, sufficiently light so that it's kinematically allowed, and B, those light particles have to be weakly coupled to the plasma such that they don't receive large corrections to their mass inside of the plasma. For example, like this photon decay, and by the way, inside of a medium photon, I'm going to call it a plasmon. This can be really efficient. There's a lot of phase space available. And this is a very well-known phenomenon in the context of stellar astrophysics, because this type of a process can actually be a really important source of energy loss for stars and can really accelerate their evolution. So just to give a concrete example of this kind of known physics process, which sort of blew my mind when I was first learning about it, Here I'm just really briefly showing the white dwarf luminosity function as a function of, so that's just the number as a function of magnitude. And you can actually try to predict what this will be based off of analytic arguments and based off of stellar evolution codes. So you can compare theory and data here, and that's what the blue and purple are doing. So white dwarfs you can think of as being the simplest example of a star, and just on a very spherical Cal level, what happens is these white dwarfs get born on the bright hot end, and monotonically over time they cool down and they move to the right of this plot. Now, if that were happening just due to surface photon cooling, right, because these are optically thick, so photons can't really escape from the inside of the star, they can only really come from the surface and cool the star that way. So if that were the main mechanism, then you would have this orange line predicting the number of stars that you would see. And from what you can see, that actually does a reasonably good job of describing the data at kind of intermediate to high magnitudes. So that actually is a really good description of the physics of what's going on, except for at very low magnitudes. You see this pretty big dip, and that dip is largely due to basically these plasmons decaying to pairs of neutrinos through an E plus E minus loop. So so I was looking at this, me and my collaborators were looking at this for kind of unrelated reasons. And we saw this and we said, well, this seems to be most efficient. This plasmon mechanism seems to be most efficient for basically the hottest, brightest stars. And so where else do we have an example of a very, very hot plasma? The early universe, it turns out, right? So we thought, why can't this happen in the early universe? And it turns out it can. So this can actually happen for sub-MeV dark matter, provided that there's some coupling between the plasmon and the dark matter. And as far as we know, this is the most efficient way of making dark matter through some sort of a thermal process in the early universe. Now, as far as how you couple these plasmons to the dark matter, one example, oops. Oh, sorry, right, before I move on to that, right, one thing I wanted to say is just to talk about the phase space. So for the early universe, it's a relativistic plasma. So the phase space that's available depends on the temperature. So here I'm showing basically on the y-axis, that's the effective mass as a function of the wave number. And you'll see that it's pretty close to the plasma frequency, which for a relativistic plasma of temperature T on dimensional grounds, again, it has to be linear in the temperature. So you can see that from this plot, the proportionality constant is roughly 0.1. And you have both transverse and longitudinal modes get an in medium effective mass. So both of them are contributing, but really it's mostly the transverse modes just because there's a wider range of K, there's more phase space. Right. So back to my point that I was going off on a tangent earlier of how to couple the dark matter to these plasmons. Probably the cleanest example is just to introduce a dark photon into the theory where if you have dark matter that's charged under some dark U1 gauge group, and if that force carrier is kinetically mixed to the standard model photon, then provided that dark photon does not pose a relevant scale in the problem, then this mixing can proceed without being suppressed, and you can have this process making dark matter very efficiently. I want to also mention that you hear sometimes a lot about charged dark matter, particularly it's become more trendy, I would say, in the past 2 to 3 years because of the edges anomaly and people trying to explain that using charged dark matter. But people don't often talk about where that charged dark matter comes from. And as far as I know, this is the simplest way of making charged dark matter, just because the freeze out mechanism that I told you about before is actually excluded. The coupling that you would need is way too high, and it's already ruled out by now. Okay, so speaking of freeze out, I want to just do a little compare and contrast now between freeze out and freeze in. So again, I'm plotting the co-moving density. Here it's in units of the number density that you would need to have the right relic abundance of dark matter. And in purple, I'm showing freeze out, and also I'm showing the electron number density. And just contrasting that with what's happening with freeze in, and you'll note that I'm plotting this for a particular choice of mass, which I'll just go into right now. So here I've chosen a dark matter mass of 1 MeV. And something that's really crucial about this is that you see kind of the timing of when freeze out is happening is very, very close to other really important epochs in the history of our universe. So first of all, neutrino decoupling happens, and also deuterium is forming. And that's sort of concurrent with freeze out occurring for this particular choice of dark matter mass. And that's bad because this population, because it has a thermal number density, it carries quite a considerable amount of both energy density as well as entropy density, which means that it's going to affect, first of all, the neutrino temperature relative to the photon temperature. Normally, the way you calculate that is through entropy considerations. So if you have some additional degree of freedom, that's going to change the relative entropy that's getting injected, comparing the photons and the neutrinos. So that's going to be one problem. Another problem is you're going to have energy injection. So you can potentially have a problem of messing up the formation of deuterium because it's not very tightly bound. So having dark matter freeze out at this particular mass is very ruled out. In fact, I believe the current best constraints on dark matter freeze out are closer to roughly 10 MeV. Meanwhile, though, what you'll note is with freeze in, so through this kind of mechanism where you make the dark matter, for example, through this plasmon decay process, it never really has the chance to achieve a thermal number density. And so it has very little energy and entropy. And so because of that, there's no issue with BBN, there's no issue with neutrino temperatures. So, for those experts in the audience, you might sometimes hear people say, well, you can't make thermal dark matter below an MeV. I would say that freeze in is kind of a key loophole to this statement, because you're making the dark matter through a process where the plasma that's making it is thermal, but the dark matter itself is not thermal. And so in that sense, it's a thermal-ish mechanism. And it's kind of the main loophole for making dark matter thermally below an MeV. So, okay. So I've just told you that this dark matter has to have basically such a weak coupling to the standard model that it can't thermalize. And so that might ring some alarm bells for people. So you might worry this is not going to be something that's testable. However, this kind of situation in particular, where you have this mixing with the photon and with a dark photon that's light, means that this actually situation is highly testable in the lab. So in spite of the fact that the dark matter coupling has to be tiny, you get a really large enhancement, like v to the -4 enhancement to the cross-section, provided that the dark photon in the theory is sufficiently light. This is completely analogous to Rutherford scattering. And the typical speed of dark matter, for instance, in our galaxy is 10 to the -3, the speed of light, which means that v to the -4 actually gives you quite a large enhancement to the cross-section for a direct detection experiment. So even though the coupling has to be really small, this is still something that you can look for in the lab. And in fact, if you go and solve like the relevant Boltzmann equations to try to say, okay, what is the coupling that I need to have in order to make the correct amount of dark matter that I observe, the parameter space turns out to look like this. So on the y-axis, I'm plotting the effective charge, which in this dark photon scenario, you can think of as being the product of the kinetic mixing times the dark U1 gauge coupling. So that's what I'm plotting on the y-axis as a function of dark matter mass. And you see this freeze-in line, again, very, very tiny coupling, right? We're talking about charges of order 10 to the -11, right? So that's really, really small. But as you can see here, there are lots of different ways of observing this. One of them has to do with stellar emission, which is similar to what I spoke about before. I talked about white dwarfs, but you can also have other kinds of stars exhibiting this kind of behavior. And in addition to that, we have, as dotted lines here, I'm showing a lot of proposed experiments, which are specifically using novel materials and gapped materials to try to basically match the kinematics of very light dark matter better, and trying to look for lighter and lighter dark matter. And actually freeze-in is a key target for these kinds of experiments. So one thing I want to note is that if I transfer this now to the direct detection plane, so instead of plotting the charge on the y-axis, if I actually plot the cross-section with the electrons in my experiment, it's really important to take into account this plasmon channel that I mentioned. So previously, you can open up the 2017, dark sectors community report. You can open that up and you can see freeze-in lines all over the place. And that's because people already knew about freeze-in, right? They already had a bunch of different models in mind. And one of them was you get freeze-in from E+ E- annihilation, again, through some sort of light mediator. That's what's shown as the red line. But if you have that kind of coupling to electrons, then it's not optional. You also necessarily will have this plasmon channel contributing as well. And that actually causes the predicted signal strength to drop, basically because if you have an additional channel of making dark matter, you had better lower the coupling so that you don't overproduce it. And so what you can see is on this plot, especially at the low mass end, like towards 10 keV, you're actually lowering the predicted signal strength by basically almost 2 orders of magnitude. So it's quite a big effect. At higher masses, it turns out not to be so relevant. So I want to just quickly highlight why that is and go through the logic of why that is. So let me start with a relatively heavier mass. Let me first start and talk about a dark matter mass of 400 keV. And I'm showing here the total relic abundance, the relic density of dark matter. And I'm breaking it down as far as contributions from these 2 different channels, from E+ E- as well as plasmon decay. And what you can see is that the plasmon decay for this mass turns off at higher temperatures, earlier times. And that corresponds to basically the plasma frequency, which you can think of as being a proxy for the plasmon mass, effective mass. Basically, when that's at threshold to decay to a pair of dark matter particles, that's kind of when this process stops being efficient. And so it shuts off at early times. Meanwhile, E+ E- in this picture can persist for much longer. And the thing that actually is relevant for shutting off that process, because here the dark matter is lighter than the electron, so it's not a kinematical thing, it's more of, what is the availability of E+ E- pairs in the initial state. And so the temperature when this process shuts off is close to when the temperature is of order the electron mass, because that's when electrons start to become Boltzmann suppressed. So for this choice of mass, the E+ E- channel is more relevant because that the point at which that process shuts off happens later. But that's not true if you drop the dark matter mass. Then basically what happens is this threshold, this point at which you have dark matter being at threshold, happens much later, and this channel is allowed to make dark matter for much, much longer. And it's an IR dominated process, as it turns out, so that can actually be really substantial. And so that's why this process is especially efficient at making light dark matter. Just to give a quick recap so far of what I've said before I move on to the cosmology side of things. So with thermal freeze out, we have dark matter particles, for example, annihilating into the standard model, which has a lot of nice properties. You have the WIMP miracle. You have things being independent of initial conditions. The cosmology of it is fine, provided that the dark matter is heavier than a few MeV, and the relevant couplings can be experimentally probed. Now, if I take this sort of schematic Feynman diagram and I just switch the time arrow, then that gives me freeze-in, and specifically focusing on the case of freeze-in via a light vector mediator and including plasmon decay, we have a lot of the same nice properties as what we had for freeze-out. Namely, the relic abundance is independent of initial conditions. As we saw, it's most of the dark matter is being made at late times. It's an IR-dominated process. This is actually fine with BBN and ineffective down to masses as light as a few keV. And moreover, even though the couplings are a lot tinier, they can still be experimentally probed and in fact are a key benchmark of proposed experiments. So that's a recap of my talk so far. For the rest of my talk, I want to really focus on constraining this parameter space using cosmology. So are there any questions at this point before I move on? If not, I'm happy to continue.
Can I ask a very basic question?
Yes.
Can you explain a little bit of why this MEV bound for the freeze out and KEV bound for the freeze in?
Sure. Yeah, let me go back a few slides. Right. So freeze out, the temperature when freeze out happens is like roughly when the temperature is like the dark matter particles mass over 10 approximately. So if you make the dark matter as light as an MeV or even as light as 10 MeV, then the freeze out temperature is kind of at like the MeV scale. And that's a very important scale when a lot of things are happening in the early universe. You have all sorts of thermal processes that are things that are measurable with existing experiments, which we've measured very well. So if you start fiddling with the physics that's going on at that time, then it's going to be basically ruled out.
Okay.
So that's where the MEV scale is coming from on the freeze out side. On the freeze in side, right? So I mentioned this sector, this dark matter particle that's freezing in, it carries very little energy and entropy, so you're not going to be able to mess with things that we can measure at this epoch. But that argument goes out the window because as you drop the dark matter number density, as you drop the dark matter mass, you have to raise the number density to compensate, basically, to give you the same total amount of dark matter. And so as you start raising that density, then it starts becoming less and less true that it doesn't have a lot of energy and entropy density. Yeah.
Basically, for freeze out, because MEV roughly BBN happening, right?
Yes.
kind of say that, but for the KeV, you are seeing which observable constraint KeV bound?
So for Friesen, it's the same kind of bound. It's also I'm just talking about MEV or BBN bounds here. I'm going to talk about other kinds of bounds like warm dark matter bounds a little bit later in my talk. Yeah.
Okay. Thank you.
Yeah. So I don't know if that's what you were getting at, but in case that was, I'm about to cover that. So in case you're worried about it.
Yeah, I think I get it. Okay, thank you.
Yeah. Any other questions at this point before I move on and talk about the cosmology? Okay, if not, then I'm going to move ahead and talk about, sorry, let me scan to this part of my talk. Right. So, okay, we're talking about cosmology and how to constrain this dark matter scenario with cosmology. And a key insight that we're going to use in order to do that is that the dark matter that gets made this way is born hot in some sense. And here hot is in quotation marks because, as I have tried to emphasize, the dark matter does not necessarily thermalize, so it does not necessarily even possess a temperature necessarily. But what I mean by hot is just that, you know, this dark matter is getting born either from E plus E minus, where the E plus and E minus are relativistic, or it's being born from decaying plasmons, which are photons fundamentally. So that's also indicating that regardless, this dark matter is going to inherit kinematics that are going to mean it's going very, very fast when it's born. The way to really quantify this is through the Boltzmann equations. And in particular, if we want to deal, if we want to deal with non-thermal phase space, then you have to deal with the full untruncated Boltzmann hierarchy. Oftentimes we're used to thinking about moments of this hierarchy, but we really have to think about the full evolution of the phase space here. So the relevant equation is this full Boltzmann hierarchy where we have a term accounting for how phase space changes over cosmic time. This term is accounting basically for ordinary redshifting due to expansion. And then this term is really where all of the magic special sauce lives. This is where all of the collisions are hiding. And I don't want to get too into the technical details here, but I'm happy to talk about it more a bit later. But basically what's living inside of here are these E plus E minus annihilations, as well as the plasmon decays. And for those of you who are experts on dealing with, you know, thermal integrals and dealing with this kind of collision term, you'll notice that the phase space factors that I have in here are not dark matter phase space factors. And the reason for that is, as I showed you a couple of slides ago, the occupation number of dark matter is substantially lower than the occupation number of basically all of the other thermal particles in the bath. And so what that means is that while Friesen is active, we can essentially ignore back reactions, right? Because the number, so for example, like inverse decays are really, really negligible because the dark matter number density is so much lower than the density of photons, which are responsible for the forward process. So we can really ignore back reactions. And because of that miraculous fact, the collision term actually is independent of the dark matter phase space, which means that we can semi-analytically integrate this collision term to get the full phase space for the dark matter. And when you do that, it ends up looking something like this. So the y-axis, I'm showing the phase space along with the usual p-squared measure. And on the y-axis, I'm plotting, this is a co-moving quantity. It's the dark matter momentum in units of the photon temperature, right? So both of those quantities scale like 1 upon A, the scale factor A. And what you'll see here is that, you know, it's highly non-thermal, right? You've got this thing that's very peaked at low momentum with a very fat tail. So what's going on there? Let me first focus on the plasmon side, which is the yellow line. So the plasmon decay story is, you know, it's fundamentally a decay, right? Which means that sitting inside of every decay is this thermally averaged boost factor, right? So what that means is that the plasmons are preferentially going to decay, quote unquote, at rest, right? When you're in the long wavelength mode limit. So what that means is that you have this peak at very low momenta. But you also have this very fat tail from these plasmons, and what's causing that is basically right at earlier times when plasmon decay is active, the plasmons have a higher effective mass, and so when they decay, right, the dark matter particles get a pretty big kick, and then as the universe is expanding and cooling, you're basically scanning through a bunch of different plasma masses, which means that as the universe evolves, the dark matter particles getting made from those decays are going to have characteristically different momenta. So that's why it has that very fat tail, that characteristic shape. E plus E minus also contributes to that fat tail as well. So at the end of the day, you end up with something that looks very non-thermal. I do want to mention, however, that if dark matter is able to self-scatter, what can happen is this initial distribution that it's born with can later thermalize in a way that basically preserves p squared, basically conserving energy within its own sector. And that can happen parametrically more quickly if you have self-interactions where you have a dark photon mediator. Just to be explicit, this process, if it occurs to this dark photon mediator, scales like g chi to the fourth, where again, g chi is this dark U1 gauge coupling strength, different from Q, right? So you have two different parameters. You have Q, the effective charge, which sets the amount of dark matter that you make, and you also have g chi, which sets the self-scattering rate. So you have a little bit of freedom here to have different parameters. But I want to point out that this is, again, a v to the -4 scaling process, and it's especially effective at late times, because as the universe is expanding and cooling, particles, their velocities are basically being Hubble damped, right? So they're going slower and slower. So you can scatter efficiently at late times. So if you wait long enough, basically, the dark matter will thermalize at some point. One way you can parameterize that is on the y-axis. I'm showing the redshift at which the dark matter is able to thermalize for different choices of the kinetic mixing kappa. So here I'm showing two lines, kappa equals 10 to the -4 and kappa equals 10 to the -3. And then I'm fixing g chi to be whatever it has to be to give me the combination, to give me effectively the charge that I need to make the correct amount of dark matter. So what you can see here is if you change kappa, if you change the kinetic mixing and then fix g chi, you can either thermalize at pretty early times prior to recombination, or you can thermalize at later times. So there's kind of some freedom there. I want to note you can't thermalize at arbitrarily early times because in order to do that, you would need a sufficiently large value of g chi such that you would actually violate observables. You would actually mess up, for instance, the bullet cluster. So there's some constraint. You can't thermalize too early in this situation, but you can potentially thermalize prior to recombination. But in either case, there's going to be some sort of implications of this phase space for cosmology. And one of those implications, as I alluded to in answering Da's question, is sort of similar to warm dark matter. So, so for just a quick recap, if the dark matter is born going very, very fast, then it's going to behave a little bit like warm dark matter. It's going to have slightly different initial conditions. So the typical initial conditions that we have for warm dark matter look something like this, where to have a fixed amount of dark matter, you have, for a given dark matter mass, you have to then fix its temperature ratio to the standard model in a particular way, so that basically raising the dark matter mass means you lower the dark matter temperature to give you the same amount of dark matter. So what that means is that for lighter dark matter candidates, for lighter warm dark matter candidates, you have to raise the temperature. And when you raise the temperature, that means that the typical sort of RMS velocity of this dark matter is going to be higher. And that's a problem from the point of view of structure formation, because if the velocity is too high, right, you have all these structures in the early universe that are trying to collapse and trying to form. But if the velocity of dark matter particles is high, then it's going to be higher than the escape velocity of these nascent structures that are trying to collapse. And so the dark matter is going to basically escape any gravitational potential that it encounters. Essentially, in other words, it's going to free stream through the cosmic web, and it's not going to cluster. And what that means is that all of these gravitational potential wells are going to be shallower than they would have been had they been able to accrete some dark matter. So you're going to smear out structure formation. The lighter and harder you make dark matter, it's going to be more clumpy if dark matter is heavier and cooler. Now, in cosmology, we're great at looking for this kind of clumping and this kind of clustering. One of the most well-known ways is using the Lyman alpha forest. So I'll just show a really quick cartoon of how this works. Basically, you have some broadband spectrum of some very high redshift quasar. And then as the light from that quasar is moving towards us, it's moving through the cosmic web of structure. And every time it encounters a neutral clump of hydrogen, there's going to be some Lyman alpha photons that are going to be absorbed by that neutral hydrogen. Now, this light is traveling for cosmologically long times, which means that as it's traveling, the entire spectrum is shifting over to the right, which means that every time it encounters a new clump of neutral hydrogen, there's some pristine, very clean part of the spectrum where there isn't any imprint yet, because the part that got imprinted has shifted to the right of this plot. And at the end of the day, you end up with this very dense forest of spectral lines, which tells you how much structure was there along the line of sight to these photons that you're observing. And this is a really powerful method of constraining structure, particularly on small scales. And this is a whole program, many people working on this. So I don't want to, I don't want to overstate this, right? There's a lot of complications here, but basically people have done lots and lots of analyses to try to understand how would warm dark matter affect this. There's another type of effect, which I'll talk about if I have time, and that's the effect on low mass halos and subhalos. So what that means is that if you have suppressed clustering on small scales equals small halos, low mass halos. And so if you have suppressed clustering, you also don't form very many low mass halos in sort of the sort of hierarchical picture, the bottom up picture of structure formation. And I would say in the past year to year and a half, we've gotten even better at looking for very small, very low mass halos and subhalos. I don't have time to talk about all these different methods, but if people want to put in the chat what they would want to hear about if we have time permitting, please feel free. So you can either vote for stellar streams, lensed quasars, dwarf galaxy counts, or 21 centimeter cosmology. So just feel free to write your preference in the chat. I'll revisit what you guys wrote later if there's time. So feel free to take a moment to do that now. In the meantime, I'm going to take a sip of my water and give you a moment to do that. So okay, I see some activity in the chat. So I'm hoping that everyone is voting or is nearing completion of their voting. With that, I'm going to move on and talk about the phase space and how that comes into this whole story of gravitational clustering. So as I mentioned before, right, you start out with this very non-thermal phase space. And if dark matter cannot self-thermalize, so in other words, if it's not able to self-scatter, what that means is that you have this very funky distribution, which has this very fat, high velocity tail. And the way that you treat this dark matter in practice is, because it's not interacting very much, you basically want to treat it like it's a species of neutrinos. So that's how we treated it in our analysis. Meanwhile, if dark matter can self-thermalize, so if it does, take its shape and then shift and become thermal, then in that case, the dark matter must have a non-trivial speed of sound, right? Because it's an interacting gas, basically, right? And so it's not able to stream quite freely. You have to treat it like it has a finite sound speed. So there's sort of slightly different ways that you want to treat these two situations. But regardless, when you put this dark matter into your favorite Boltzmann solver, we used both class and CAMB. What happens is you get this suppression of the matter power spectrum. Here I'm plotting the power spectrum normalized to what you would get in CDM, cold dark matter, as a function of wave number k. And you can see this characteristic suppression of structure, particularly on small scales. And what you'll note from this plot is that I'm plotting the freeze-in scenarios for both the non-thermal and the thermalized case. And I'm also plotting the suppression from warm dark matter. So a couple points to note. First of all, the exact shape of this suppression depends a little bit on whether the freeze-in is a non-thermal one or a thermal one. The thermal one looks a little bit more like warm dark matter, which perhaps is not too surprising, because in warm dark matter, you're assuming that the dark matter also has a temperature, right? So then it becomes just a question of how do you map the temperatures for the two dark matter scenarios? So maybe that's not too surprising. The non-thermal case has a little bit of a shallower decline. But one conservative thing that you can do is you can match at this sort of scale where there's this suppression at the level of 50% between the two power spectra. That's shown as a dashed line here. And people have studied this and have found that you can conservatively basically take warm dark matter limits and apply them to other dark matter theories, provided that this decline is a little bit shallower. So it turns out, yeah, when you do data analysis of different dark matter suppression shapes, this is basically a kosher thing to do. So that's one thing to note. Another thing to note is that you'll notice that for freeze-in, the masses that we're constraining or that are matching the warm dark matter case are actually higher than warm dark matter. And that turns out to be because again, physicists are bad at naming things. The nomenclature is a bit ironic, but freeze-in dark matter is actually hotter than warm dark matter. So that's why those masses are actually a little bit higher. Okay, but given everything I've told you and given the existing probes of structure formation, we can take limits on warm dark matter that are very well studied and well established and port them over to freeze-in, provided that we do this matching correctly. And so what we found was that with current data, you can go up to a limit of roughly 16 or 17 keV, with the exact number depending on whether you've thermalized or not. I want to talk very quickly about a different kind of effect, which is not due to gravitational clustering, but rather is coming from dark matter baryon drag, which is something that's present at some tiny level in this model. So, okay, I want to really briefly talk about the physics of what's happening in the CMB with baryon acoustic oscillations. So I'll just give you the cartoon picture in configuration space. So what that looks like, whoops, sorry, my computer froze for a moment. Can you guys still hear me? Can I get a thumbs up if you can hear me? Okay, I see Marcus giving me the thumbs up. Sorry about that. Anyway, this is the cartoon picture of what's going on, right? We have some gravitational potential well laid down for us by your favorite theory of the early universe. Maybe that theory is inflation, maybe it's some other theory. But regardless, we have some initial seed perturbations. And then what's happening is that matter wants to fall into those fluctuations. Now, in the case of the photon baryon fluid, right, that wants to cluster, that wants to fall into these gravitational potential wells. However, it has radiation pressure to contend with. Basically, the baryons want to fall in, but the photons are so numerous and so tightly coupled that they're bouncing around, and they're basically bossing around the baryons and pushing them out of these potential wells. So you have competing effects here between gravity, pulling things together, giving you compression, and radiation pressure bouncing things out. And that, those are competing effects. And meanwhile, what's happening with the dark matter is the dark matter does not feel radiation pressure, at least we don't think. So it's basically just able to sink down to the bottom of the gravitational potential well, totally unhindered. And that actually leaves an effect on the photon baryon fluid, which we observe in the CMB, right? Because by having all this dark matter at the bottom of the potential is now steeper. So gravity is a little bit stronger, which means that in the sort of tug of war between gravity and radiation pressure, gravity is sort of winning. And so that's the sort of canonical situation of what's happening with collisionless dark matter. But now, if you add some component of dark matter that's able to interact a little bit with the photon baryon fluid, what happens is that sometimes dark matter particles get kicked out and basically get dragged out by the photon baryon fluid. And in doing so, you're basically making the gravitational potential shallower than what it would have been otherwise. And so now gravity is not quite as strong as it would be. And that means that, first of all, when things are trying to cluster together, your compression isn't as strong as it would otherwise be. And then when things bounce, because you didn't have as much material there, the bounce is also weaker. So basically, overall, what you tend to see is on small scales, you see a suppression of basically the CMB of the modes that you would see ordinarily. This is particularly true if you have v to the -4 scattering, which is relevant for freeze-in, because things at this epoch are moving really slowly, right? At around the time that's most relevant, the time of recombination, things are moving slowly. So just to be explicit about, again, the role of the phase space, in the case where you have non-thermal dark matter, there's a lot more particles that are moving slowly, which means that because of the v to the -4 scaling, you're going to have a bigger scattering effect as compared with the thermal case, where on average, like the peak of the distribution has particles going a little bit faster. So one way to see that that effect is going to be different for these two cases is to look at the dimensionless drag. So here I'm plotting the drag rate, arc-high, normalized by the Hubble parameter. And so if this is basically order 1, then that means that the drag is completely taking over the dynamics of what's going on. And you can see that the drag rate, if you have cold initial conditions, is the strongest because you're basically setting v, like you're taking the limit v goes to 0 for v to the -4. And it gets progressively weaker when you go to freeze-in with non-thermal initial conditions. And then when you thermalize, it gets even weaker. So the effect that you see on the CMB, right? So you'll notice here that this dimensionless arc-high is of order 10 to the -2 or so. So it's a percent level effect. And with the CMB, we're able to see these kinds of percent level effects. So just to show explicitly what that looks like, again, you see that when you compare the change in CL that you get compared with the lambda CDM CL in percent, it's again like roughly a percent level effect. And it's the biggest shift for the cold initial conditions case. So given existing data from the Planck 2018 dataset, we think we can actually set a limit, a pretty strong limit, going even slightly tighter than the limits coming from gravitational clustering and from the motions of dark matter, and going up to almost 20 keV with Planck 2018 data. And this is going to improve in the future using things like CMV stage 4 to basically measure this dark matter baryon drag even better, as well as other probes, which are going to basically do a much better job of measuring clustering on very small scales. I see that I'm running a little bit low on time, so I'm not going to revisit these points that people voted on unless people ask me about it in the Q&A, which I'm happy to talk about. But let me first wrap up my talk. I just want to quickly remind you all from the beginning portion of my talk that a lot of this parameter space is a key benchmark for direct detection. So I think this is quite a nice situation where we have all of these ways using cosmology of constraining this dark matter production mechanism from basically the low mass end and moving upwards. At the same time, with direct detection, we're starting at higher masses and moving downwards. And so there's going to be some overlap between the two, which means that there's going to be basically no room for this dark matter theory to hide. So, either what we're going to see happen is it's either going to be, I think, definitively detected, but more likely, we're going to rule out all this parameter space, but, we are going to be able to find out one way or the other. And I think that that's incredibly exciting. So with that, I'll just quickly summarize the talk, which is that dark matter could be made of through a process called freeze-in and could be made of decaying light. And as far as I know, that's the simplest way to make charged dark matter in the early universe, because freeze-out is excluded for charged dark matter. This mechanism is actually a key benchmark for direct detection experiments, particularly below the MEV scale. And the precise way in which this dark matter gets born means that it has this non-thermal phase space, which leads to all sorts of interesting cosmology. So both warm dark matter types of behavior, not exactly the same, but kind of analogous, as well as dark matter baryon dragging type of effects. So I want to also just conclude by saying something, a little bit optimistic, namely that it's a big universe out there. I know that with everything going on in the world, right, it's easy to lose perspective of that, but it's really kind of amazing that we're here in this universe. And there's lots of complementarity between different kinds of systems. There's a great diversity of different kinds of astrophysical systems, which means you have a lot of room to have fun and do something creative. So in this case, being inspired by things happening inside of stars, applying it to the plasma of the early universe, and then basically pressing play and seeing how the universe will unfold and what the effects of that are going to be. So I think that's really quite fun. And so with that, I thank you all for your attention.
Let's unmute and clap for a very nice talk. Yeah, so questions?
I have a question. Can I make some comments about the difference between this scenario and the scenario that in something like a interaction with neutrinos and I forgot the exact scenario, but something that can also give you a benchmark for the sub-MeV.
Sorry, can you repeat that last part? It can give you what?
Can also give you sub-MeV, but with interaction with neutrinos, something like that.
Yeah, so there's a couple of production mechanisms for making like sterile neutrinos, which those are also not thermal. So yeah, when I say there's a couple of loopholes for having like no dark matter below an MEV, this is a thermal-ish scenario, but then you also have the sterile neutrino mechanisms, which are usually people talk about like either Doddleson-Widrow, which is sort of thermal, or Shea-Fuller, which is not thermal, it's more resonant. But both of those cases, I think the Doddleson-Widrow case is quite constrained. Shea-Fuller is, because of the way the phase space looks, it's a bit less constrained, but I think that's one of the main benchmarks for sterile neutrino searches. Yeah.
I'm not about. Oh, maybe it's Doddleson neutrino. It's similar with neutrino, something like that.
Yeah, I believe that's how the Dawson-Widrow mechanism works.
Oh, yeah, sure. Okay. Thank you.
Yeah, in fact, we were also inspired by that mechanism. So yeah, there exists a mapping, right? There exists a mapping between that scenario and our scenario. It's a little bit funky, but right, if you're able to thermalize with neutrinos, right, then you basically have a temperature that's the neutrino temperature. It's going to be like, 4/11 to the 1/30, some funky prefactor times the photon temperature. And so if you say the dark matter has that same temperature, then you can basically map warm dark matter constraints onto a constraint for Dawson-Widrow mechanism. And in that case, because the temperature of the dark matter, I think that actually tends to translate to a much stronger bound than the warm dark matter bound. Like for example, I think the existing limits on Dawson-Widrow are kind of in the 30 to 40 keV range.
Okay.
So our freezing scenario is a little bit cooler than that, which is why the bounds on our case are not quite as strong as they are on the Dawson-Widrow mechanism.
Okay, thank you.
Yeah.
Can you show your 21 centimeter slide?
Sure. Whoops. Oh no. Oh no, hold on. I messed up my fancy presenter. Okay, hold on. Yeah, so I can just quickly, I had a few slides on this actually. I can quickly talk about it. But before I talk about that, are there any other questions people want to ask first that are more pressing? If not, I'm happy to talk about this too.
I don't know if this is more pressing, but maybe it's a little bit more general. So I'm trying to sort of understand at the sort of rough level the relation between this and warm dark matter constraints. So let me just say a few things, and you can tell me if I'm completely wrong, just to see if I'm thinking about this right first. So in warm dark matter, right, in freeze out, you always are freezing out somewhat below the dark matter mass. So sort of initially you have some temperature, which is some velocity, which is not so far, which is some pretty much fixed number. Then it's a question of how much things redshift.
Wait, really quickly, I just want to interrupt you really quickly, because for warm dark matter, the way you get the initial conditions that I'm plotting here, or that I'm showing here, the way you get these initial conditions is assuming that the dark matter freezes out while it's relativistic.
Oh, while it's relativistic.
Mm-hmm.
So, but I mean, I thought that was sort of a warm, I'm thinking of the warm dark matter, what's called the warm dark matter constraint at a KeV, right?
Mm-hmm.
So my understanding is that the problem there is that a KeV mass particle, while it's about as non-relativistic as, say, 100 GeV dark matter particle at its freeze out, it just doesn't redshift as much. So, when once structure formation gets started, it still has some velocity, and you've got the free streaming problems and so on. Okay, right. Okay, now in your freeze-in scenario, right, it's kind of approaching the same. There you also have this bound of a KeV, and I think it's just because you're approaching the same bound kind of from the other direction, namely the dark matter sort of heating up as it becomes in contact with the standard model, right? And as its sort of density is set, it's set roughly by the temperature of the standard model bath at the temperature where that happens. And so it's not a coincidence, yes, that it's really the same bound, right? But then,
yeah, I think that's true. To order unity, I think that's pretty good.
Obviously, I'm not yet.
Yeah.
Now you're looking at these bounds for heavier freeze-in masses, and so my question is I guess in the case of freeze out, the heavier masses, the temperature of the dark matter, the velocity of the dark matter, if you like, is redshifting so fast that almost very quickly above a KeV mass, the dark matter is just super cold. Is that correct? Whereas this freeze-in thing still has some more. This is the difference. That is this a key difference, that the freeze-in case has more sort of internal velocity left over, and that's why you have these additional observables?
Yeah, I guess I would say that the point at which the two sectors, like the dark matter and the visible, like standard model plasma, the point at which they decouple If you look at, so again, the dark matter isn't necessarily thermal, so you can't necessarily talk about temperature, but
Right.
like let's say talk about like p squared, you know, like some sort of RMS velocity, and take that as a proxy for the temperature or the internal energy. And when you compare freeze out versus freeze in, like warm dark matter versus freeze in, the freeze in case for a fixed mass, for fixed dark matter mass, has a little bit more of a kick to it. They both redshift the same way, like after decoupling, right? Momenta redshift like 1/a for both cases. It's just that the freeze-in case starts with a little bit of a higher typical velocity.
So it really comes in down to the details of the shape of the distribution, thermal versus the one for, but other than that, there would be similar bounds, maybe not quite as strong for light dark matter from freeze-in.
That's true, yeah.
Okay.
Yeah, so I think in most
I
cases,
just wanted to make sure I was getting the big picture. So thank you.
yeah, no, absolutely. I also want to note, like, yeah, in most cases, a lot of the times in the literature, you'll see people applying the warm dark matter limit to any old dark matter candidate. And most of the time that's like actually not appropriate to do that at the, like, you know, at the, you know, 2 significant digits level. Like that's not an appropriate mapping to do. If you only care about order unity, then like that mapping is perfectly fine. But there can be problems sometimes when people do that mapping and they're really trying to live near the boundary of that limit, right? Then that becomes kind of a problem. And I think that there is quite a swatch in the literature where people do that. And I think that's probably kind of problematic and probably ought to be revisited. Yeah.
Okay, I think why don't we go to the 21 centimeter question? Tell us about 21 centimeter.
Sure, so I'll just quickly do my spiel. Of all the spiels, it's the longest spiel, so just letting you guys know that in advance. But how that works for those who are uninitiated, basically the 21 centimeter line comes from this flip transition where you can either be in the excited state and basically de-excite, emitting a 21 centimeter photon, or you can have absorption, the reverse process. And in practice, whether we see in our universe, whether we see gas in emission or absorption, basically depends on a bunch of different temperatures and what the relative ratios of those temperatures are. So first of all, there's the kinetic gas temperature. That's like the PV equals nRT temperature. There's also the CMB temperature. So the CMB you can think of as being a backlight to these 21 centimeter photons. And finally, there's something called the spin temperature, which is not a real temperature in a sense. It's just a measure of how many particles are in the excited state versus the ground state of this 21 centimeter, like are they in the singlet or the triplet essentially? And so that you can think of that temperature as being like the log of the ratio of the ground state to the excited state. So there's a lot of complicated physics going on. I'll just walk through it really quickly, super quickly, and talk about it in terms of the on average, sky average global 21 centimeter signal, which looks something like this. So starting at early times on the left, what's happening is at early times, the spin temperature is very coupled to the kinetic gas temperature, the PV equals nRT temperature, because the gas is pretty dense. There's frequent collisions which couple these temperatures. And so because the kinetic temperature is lower than the CMB temperature, basically the reason for that is because the gas at this point is non-relativistic, right? So its velocity scales like 1/a, which means the temperature, which scales like the RMS velocity squared, that temperature scales like 1/a squared, whereas the CMB temperature scales like 1/a because these are relativistic, because the photons are relativistic particles. So the kinetic temperature is less than the CMB temperature, which means that compared to the CMB backlight, we see the signal in absorption. But that doesn't persist forever because at some point the density of the gas drops. These collisions are no longer very frequent. And so at that point, the spin temperature of the gas is more coupled to the CMB temperature, which again is quite a bit bigger than the kinetic gas temperature. So you stop seeing very much of a difference between the CMB backlight and the spin temperature. So you basically, your signal starts to go to 0. Then what happens is the spin temperature is driven towards the kinetic gas temperature by a process called the Wolthuisen field effect. You can think of it as being kind of akin to like optical pumping for lasers, but it's basically an effect where If you have a lot of Lyman alpha photons, then you just drive the population such that the spin temperature is similar to the kinetic gas temperature. And so because this whole time the kinetic gas temperature has been really dropping compared to the CMB temperature, then you start to see a really deep absorption feature. Again, this doesn't persist forever because the same sources that are emitting all these Lyman alpha photons, which are causing this coupling, this poison field effect, those same sources are going to start heating up the gas. And so now the kinetic gas temperature is not scaling like 1/a². It's not adiabatic. It's actually heating itself up. And at some point, it's even getting hotter than the CMB temperature. So at some point, you start to see the signal for the first time in emission rather than in absorption. And then these same sources that are heating up the IgM, intergalactic medium, start to reionize the universe, and the signal strength starts to taper down. So that's what's happening. And that whole time, you're depending on sources of radiation, which are basically driving the dynamics of whether you see the signal in absorption or emission, and how big of a signal that you see. And these sources emitting these Lyman alpha photons that are responsible for reionization, those sources are depending on structure formation, essentially, to be able to form. So if structure formation isn't happening, those sources can't form, which means that this has some bearing on the question of how much clustering am I having on small scales. So if you have warm dark matter, you have fewer low mass halos, which means that this sort of whole process gets delayed. And I apologize between these two plots. They're from different authors. On this plot, early times are on the left, and on this plot, early times are on the right. So sorry for that. But if you have warm dark matter, this whole process of sources heating up the gas and coupling various temperatures, that whole process gets delayed. And so that's why this absorption feature shifts relative to CDM. And so that's something that's observable in the sort of sky averaged global signal of this observable. If you start to do the same thing or apply similar arguments to the power spectrum, it's even more powerful. There was a study that came out a little over a year ago, basically showing that with an experiment like Hera, which is online and which is taking data right now, we're going to be sensitive to warm dark matter masses of roughly 14 keV. And luckily, this is actually on a scale. This is on a length scale where it's happening inside of a halo. And so a lot of the degeneracy with astrophysics is not really relevant on those scales. In other words, you're decoupling from the sort of uncertainty surrounding like what's happening in the intergalactic medium at large. And so you can potentially go all the way up to 14 keV warm dark matter limit with this kind of mechanism. And so then it becomes a matter of mapping that onto Friesen. And that's where we get the limits that I think I showed towards the end of my talk. Happy to also discuss if there are any questions about that.
So these other things that people talk about for 21 centimeter, they're not going to be relevant?
Other things, you mean like global signal experiments or?
There's all, what's it called? The square kilometer array, and there's something else too.
Yeah, so there's like the SKA, there's also like, yeah, there's a lot of different 21 centimeter experiments. There's CHIME, which is doing lower redshift. There's SKA, which is still pretty futuristic as far as whether we can really say anything robust about what SKA is going to do at this point is, I think there's a big question mark there. But yeah, there's a lot of other experiments that are global signal experiments. So Hera in particular is looking at fluctuations. So looking to try to make a power spectrum measurement, which is a little bit different from the more simplified thing I just showed you, which relates to the global signal. But yeah, as far as global signal experiments go, there's a ton of them out there because they tend to be very cheap instruments to build. So there's EDGES, which I already mentioned. There's like 6 or 7 experiments. There's like SARAS, there's like LIDA, PRISM, HIRAX. I'm sure I'm still missing several. Like there's a lot of these experiments.
You're telling me I should just forget about them?
Well, I think, so if you have fluctuations, so I'm sweeping a little bit of stuff under the rug in terms of astrophysical degeneracies with the global signal. If you have fluctuations like with Hera, then you actually break a lot of those degeneracies. And so it's actually quite a bit more powerful. So yeah, don't forget about them. They're still doing really good and important science, but at least for this particular application, Hera is more relevant.
Thanks.
Other questions?
Can you make some comments about the non-Gaussianity measurement at 21 centimeter?
Okay, sorry, non-Gaussianity, like as far as like primordial non-Gaussianity, or?
Yeah, primordial non-Gaussianity. Yeah.
Mm-hmm.
So is this people talking about like 20-watt tomography is Hera or is SKA?
Sorry, are people talking? I think my internet connection was a bit weird just now. Are people?
People talking about the cosmology collider physics, and the main observable is from 21 centimeter measurement. So is this also Hera?
Is this, sorry, there's like some crackling I'm hearing.
Is Hera the experiment that's going to tell us about some of the things that people are talking about in like cosmological collider physics? I think that's the question.
Yeah, so yeah, sorry about that. There's some crackling on your end. I don't know what the deal with that is that I'm hearing. Sorry about that. Yeah. Yes, Hera is one of the experiments that people are talking about for doing cosmological collider physics. Absolutely. Yeah, and I think one thing that people don't always appreciate is that it's built, it's taking data right now. People, I think, are used to 21 centimeter as being something very futuristic and very far off, but no, it's here. You know, as far as I know, and actually, I should mention that, you know, McGill is a partner institution in Hera, so, you know, I'm not totally unbiased here, but as far as I know, that they're going to be releasing a first upper bound on the signal fairly shortly, which was based off of, you know, basically while they were building the full array, right? So they build a few elements of the array, right, first, and those were taking data while they were still building the other elements of the array. So based on the incomplete array, they're going to be putting out a first limit, I think, probably within the next few months.
Okay.
So it's, yeah, it's here.
Yeah.
The time is now. I'm very excited about 21 centimeter cosmology.
Yeah, because we are talking about this, that's when people usually think about 20 years later or 30 years later.
Yeah, so certainly for like something like the SKA, that is quite a bit more futuristic.
Okay,
yeah.
good to go. Thank you.
Yeah.
Okay, I'm going to suggest we thank Katelin, and we'll stick around after the recording stops for some more discussion. Let's thank Katelin again.